What we're going to do now is we're going to form some ions. So forming ions. Why do ions form? Well, ions form because the atoms like to become as similar as they can to the nearest noble gas. Remember those noble gases in the 18th group on the periodic table? They didn't react, they didn't explode, they didn't go on fire, they just kind of were calm, cool, and collected. And if you remember about those noble gases, they had full outer energy level. So their valence energy level was completely full with as many electrons as they possibly could take, and those electrons were paired up. They were in pairs. So elements try to become similar to the nearest noble gas, and how they do that is they want to try to fill up their energy level to the maximum number of electrons that they can hold. Okay, so why they form, we're going to put down that atoms try to become similar to the nearest noble gas. And what they want to do is they want to fill their outer energy levels. Right. Now, sometimes in order to have full outer energy levels, they actually have to get rid of some electrons. So that's what we're going to be doing here. All right, so let's start off with something simple like our sodium. So we're going to go back, do a Bohr diagram, then do a Lewis diagram, and then I'll tell you how it becomes an ion. So with our sodium, we start off with 11 protons in the nucleus and 12 neutrons in the nucleus. All right, we've got our electrons, our first two out here in the inner energy level, and then we've got our next energy level here, and we've got 1, 2, 3, 4, 5, 6, 7, 8. So that energy level is nice and full. All right, so it kind of looks like a noble gas, doesn't it? Except in this particular case, we still have to put one more electron out here. Right, so we've got one out here. So in order for sodium to look like the nearest noble gas, which just so happens to be neon, we're going to see a lot of neon in this. So the nearest noble gas is neon. It would have to lose this electron in its outer energy level. So this one that's way out here, it's going to have to be gone. And then that way, when you look at the inside, right, with this one gone, the inside here looks like neon. Right, so you want those outer energy levels to look like neon's outer energy level. It wants to look like a noble gas. Even though it's not a noble gas, it's still sodium because it still has 11 protons, but on the outside it looks like neon. Right, so let's do this next step here. So because with our Lewis diagrams we only have to draw the outer energy level, which is sodium, we only have to put one electron here. Now, sodium is going to lose that electron that's in that outer energy level. It's really difficult for this nucleus to hang on to one electron that's way out there in that outer energy level. So if something comes by and it tends to like electrons, this electron's just going to leave. All right, so same thing. This is exactly the same diagram. It's just a Lewis diagram. That electron's going to be gone. Right, it's gone now. Now remember here, we've shown that this electron's gone, but keep in mind the next energy level here is full of electrons. So just like we drew here, all right, but we didn't have to draw all this in because we know they're there. So now what we've got is we've got our sodium, right, our core of sodium. It's lost an electron from the outside, so it's no longer a regular sodium ion, or atom. So to show that it's an ion, we're going to put square brackets around the outside. So this means that something has changed, and when we're doing our ion diagrams, the only thing we need to show on the inside around here is that outer energy level. Now that outer energy level for sodium doesn't have any electrons in it anymore, so we don't show anything, we don't draw anything in there because that outer energy level that would be around here is now empty. However, we just lost an electron. Think about this. Our charge on our atom here used to be 11 protons, 11 electrons, and it was equal. Now we've lost an electron. So our overall charge is going to be positive because now we have 11 protons, but we only have 10 electrons. So our overall charge is going to be positive 1 because we've lost a negative electron. I always like to say when you lose a negative electron, it's like losing part of a negative attitude. You become a little bit more positive. All right, so we've lost our negative electron. We have an overall charge of positive 1 because we lost 1 electron. Let's do magnesium next. All right, so with magnesium, we've got 12 protons in the nucleus and we've got 12 neutrons. All right, we've got our outer energy levels, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But we still have 2 electrons to put on the outside here. Now, if you're looking at this, all right, this energy level is all full. It's got 8 electrons. It looks an awful lot like neon. So this is what magnesium would like to look like neon on the outside. But no, we've got these 2 electrons out here taking up space. All right, so if we were going to draw this as a Lewis diagram, we would draw it Mg with 1, 2 electrons. So what do we do? Now this again is really difficult for this nucleus to hang on to all these electrons plus these 2 little stragglers on the outside. So if something comes along and can take those electrons away, can rip it out of there, it will. So this electron can be gone and this electron can be gone. And if we remove those 2 electrons, then the outermost energy level here has 8 electrons in it and it looks an awful lot. Again, like I told you, we're going to see neon a lot. Looks like neon. So same thing here. If we just ignore that we have the Bohr diagrams here, if we were just doing Lewis diagrams, this electron would be gone and this electron would be gone. And we would remember that the next energy level that would be drawn in here, all right, would be full of electrons. So now, it's no longer magnesium. It's lost, well, it's still magnesium, but it's no longer a magnesium ion. It's lost, or atom, because it's lost those 2 electrons. So now we're going to draw it as an ion. We're going to have Mg in the center. Right, our square brackets around saying this is no longer an atom, now it's an ion. It's got square brackets around the outside. Now, as you progress through science, you won't be needing to draw these square brackets around the outside. This is just for right now while you're learning. The outer energy level that we always show doesn't have electrons in it, so we don't show anything in it. So with the metals, we don't show anything in the outer energy level. And now this guy lost 2 electrons, so it lost 2 negative attitudes, or it lost 2 negative electrons. So its overall charge now is going to be positive 2. Right. So now this magnesium, it's satisfied. It has an overall charge of positive 2, and that's going to be really important for our next lesson. But now it's satisfied. It has 8 electrons in its outer energy level, even though you don't see it because they're all in here. Okay. So let's take a look now at the non-metals. Let's do the same thing now with our non-metals. Get the paper out of there. So with our non-metals, let's do fluorine. Okay, so our fluorine here has 9 protons. It has 10 neutrons in the inside, all right, in the nucleus. It's going to have 9 electrons around the outside. So 1, 2, and then we have to put 7 in this outer energy level here. 3, 4, 5, 6, 7, 8. There's 9 in altogether. All right, so remember we said these little unpaired guys always cause the trouble. Look at this guy, paired, 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 unpaired. If we were somehow able to put another electron in here, wouldn't that look an awful lot like neon again? All right, now, so I said we're going to use a lot of neon here. So if we could somehow fill that outer energy level, it would look like neon on the outside. It would still be fluorine because it still has 9 electrons, but on the outside it would look like neon. So let's draw the Lewis diagram for this. Okay. Now, wouldn't that be convenient if there happened to be some electrons that were zipping around, like say from this page, all right, and it managed to be able to boop, end up in here. So we have it, I'm just going to do it in red just so that you know that this is the electron that came from elsewhere. So if fluorine's around somewhere and there happens to be something that tends to get rid of electrons, and fluorine needs an electron and it can scoop it up, it's going to, all right? So now on the outside, this looks a lot like neon on the outside, right? It's fluorine on the inside, but it's neon on the outside. So same thing here, if we were just do it with our Lewis diagrams. If this little fluorine was sitting here, it has a spot for one extra electron, and oh, there just so happens to be some electrons flying around from this page. The electron's going to come in here and be there. And then look at that. That is like a perfect outer energy level, nice and full of electrons. But it's no longer an atom because it's been changed. So we're going to draw our fluorine. All right. But this time, because we have to show our outer energy level, we're going to put it in brackets, we're going to have to show all the electrons around the outside. So 1, 2, 3, 4, 5, 6, 7, and I'm only going to do this in red just to remind you that this was the new guy that got brought in. All right, it doesn't matter if you do it in the same color, it doesn't matter at all. All right, so now this guy has one extra negative electron, so the overall charge on this ion is going to be -1 because we became more negative. We became more negative by 1 electron. Let's do the same thing now with let's try our, let's do oxygen, okay? So we've got 8 protons, 8 neutrons in the nucleus. All right, around the outside now we need to place 8 electrons. So our first energy level is going to have 2, and our second energy level is going to have 6. All right, so 1, 2, 3, 4, 5, 6. Look at these two little unpaired guys down here, right? You know those guys are going to cause a problem because the electrons need to be paired up in those energy levels. Alrighty, so this guy is going to, if he could get an electron here and an electron here, it would look an awful lot like, once again, neon. It would look like neon on the outside. There would be 8 electrons in the outer energy level. They'd all be paired up. It would be all stable on the outside, still be oxygen because it still has 8 protons in the inside, but on the outside it would look like neon. So if by chance there happens to be some electrons kicking around from somewhere, well, we can have an electron that goes in here, an electron that goes in here, all right? And then look at everybody's paired up, and we have 8 electrons in that outer energy level. Looks an awful lot like neon again, right? So let's try doing the same thing with our Lewis diagram, because we don't want to have to draw these guys out all the time, but I want you to understand that those inner energy level, like what's happening with those other energy levels. So this is our oxygen. All right, it's got 1, 2, 3, 4, 5, 6 electrons in its outer energy level. We've got those 2 little unpaired guys that are causing all sorts of trouble. And if we've got electrons that come in from somewhere, one can go with this guy, one can pair up with this guy. All right, it's coming in from somewhere. So if oxygen is near something that tends to give up electrons, it's going to rip up an electron from, or rip off an electron from one of those things that tends to give it off. But now oxygen is no longer an atom. It's an ion now. All right, and like I said, you're not going to have to draw those square brackets around all the time. It's just for now. But we know the core is oxygen in here. Right? And now, because its outer energy level is full of electrons, we got to draw it full of electrons. 1, 2, 3, 4, 5, 6. I'm going to do these 2 guys in red. You don't have to, but that'll just remind you that you got those 2 electrons from elsewhere. And now our overall charge, because we have 2 negative electrons that came in from somewhere, our overall charge is going to be -2. Alrighty, so what's going to happen on our next lesson is we're going to be having a little love affair here. You know how they say opposites attract? Well, look, we've got negative guys over here, and we've got positive guys over here. All right, we've got our metal and our non-metal, metal, non-metal, opposite. Positively charged, negatively charged, opposite. So I think we're going to have a little love affair in here between these two things as they match up. And as you can tell right now, just from looking at this, look what happens. We have a positively charged metal, +1, and we've got a negatively charged non-metal, -1. If these guys can be electrically attracted to each other and form a compound, right, between these two things here, we form a compound. Look at the overall charge, +1 and -1, the overall charge becomes neutral. Same thing here. We've got our magnesium, +2, it's a metal, it's +2. Our non-metal, -2. We've got these two guys that may be attracted to each other because their opposites attract. And if you look at your overall charge, you've got +2 here, -2 here. It ends up being a neutrally charged substance, right? Something to think about for next time. But just overall, what I want you to remember is that metals lose electrons, okay? And non-metals gain electrons. All right, so if you lose electrons, you become positive, and if you gain electrons, you become, negative. I said electron and I started to write down electron, right? So if metals lose electrons, they become positively charged. Non-metals gain electrons and they become negatively charged. Alrighty, so that's it for now. Oh, there's a worksheet with this, so get that finished. Talk later.